Multivariable calculus, we're looking at section 15.4, and we're investigating double integrals using polar coordinates. This problem that we're wrapping up with, this last problem of the notes, is actually a review of an exact problem that you might have done in BC Calc. Of course, without using a double integral. Ultimately, you're trying to find the area of, say, one loop of a four-leafed rose. And the equation could be r equals cosine of 2 theta. Well, what you want to remember up here is that when your integrand in a double integral is just a 1, when that surface is considered to be a 1, you'll actually get the area of the enclosed region that you have on the base. So we can take a problem that we did last year and apply multivariable calculus to it. Let's do that. You can see what I've done here. I actually graphed one of the petals of the rose, and of course you could very quickly do that with your graphing calculator. I hope that wouldn't take you too much time. But you might remember even last year we'd let r equal 0, and we would solve to find the angles for which that would make it true. So we could say, what if we had the cosine of w, for example? Cosine of some angle is 0. It only is going to take you a moment to realize that would be at pi over 2 on the unit circle, but of course we could also be pi radians directly across, 180 degrees directly across. So when you can connect your two angles with a straight line, you can just say plus pi k. And of course, w is really 2 theta. And if I were to divide by a 2, I'd get theta equals pi over 4 plus pi over 2k. And it's at this point where we can try to find the angles that would entail one complete loop. Well, obviously we'd like to at first think about pi over 4. But you might remember that when we were graphing these petals in the past, we'd also like to use symmetry. We did that quite a bit. This theta equals pi over 4 plus pi over 2k. If we let k equal 0, we'd get pi over 4. But if we'd let k equal negative 1, you could very quickly get negative pi over 4. Now I'm going to leave it to you to confirm that that actually is correct if you want to check it on your calculator. If you had theta min and theta max at negative pi over 4 and positive pi over 4, you could quickly see the petal that you'd get is what's depicted right up here. Now, in yellow would be an enclosed area of one leaf. You might notice I've drawn a little red segment there too. And I guess what I want to tell you is that R would be bounded between 0 at the origin, at the pole, and this curve cosine of 2 theta. Why am I bringing that up? Well, our area we just saw would be this enclosed region 1 times dA. Whenever we are working with polars, our dA could become r dr d theta. And then, of course, ignore the 1. What are our boundaries for dr? Well, r would be going from 0 to the cosine of 2 theta. How about our boundaries for theta itself? Well, we'd have negative pi over 4 to positive pi over 4. And now we can go ahead and actually proceed with our integral. Antiderivative of r with respect to r would be a 1/2 r squared. And then, of course, we will use our fundamental theorem here. And we'll have to finish that inner working right there using that fundamental theorem, plugging in a cosine of 2 theta. Well, you'll get that squared, of course. So we'll have our 1/2. We can leave that out in front. And we'll have the cosine squared of 2 theta. Obviously, when we plug in a 0, that minus is going to, go away. So you can see more or less we're just left with this integral of 1/2 cosine squared 2 theta from negative pi over 4 to positive pi over 4. Now, if you were asked to work this out by hand, you'd have to use a power reduction formula. That's something that we did do in Calc BC, and it's fine. You could work it out. In general, it's, the cosine squared of w would be 1 plus the cosine of 2w all over a 2. And, we'd have to, if we had a 2 theta in here, this would be 2 times 2 theta would be a 4 theta, and so forth. Could we work it out? Of course. But we could also use our calculator just to finish this work up, whether it's on the 89 or whether it's on the 84. We would just arrive at an answer of pi over 8. I will let you confirm that. But that wraps up this lesson.